Hi everybody, in this video I'm going to go over what isotopes are and how to calculate average atomic mass. So first of all, let's just consider that helium is an element that has two stable isotopes, okay? So here I'm going to use black to represent protons and red to represent neutrons and blue to represent electrons. Okay, so here's an image of our two isotopes of helium, okay? This first isotope would be called helium-3, okay? And we're gonna notice it has two protons and one neutron. This other isotope would be called helium-4. This isotope has two protons and two neutrons. And these are both stable isotopes for helium. Now, what an isotope is it's two atoms that have the same number of protons but a different number of neutrons, okay? So isotopes have the same number of protons but a different number of neutrons. And since they are the same number of protons, the proton is what determines the element. So if they have the same number of protons, that means they're the same element. But notice that they're going to have different neutrons. So helium-3 and helium-4 are both isotopes of helium. They have the same number of protons, both of them have two, but they have different number of neutrons. Okay? You could also represent this with an isotope symbol. So sometimes you see this written out. This is like the name of the isotope. You can also see an isotope symbol. So isotope symbols have the mass number on top and the atomic number on the bottom, okay? So for example, for helium-3, we would write this as helium-3, 2. And this would be helium-4, 2. And again, that 4 represents the mass number, which is the protons plus neutrons. And the one on the bottom is our atomic number. And so that's just the protons. Okay? So you should be able to identify what isotopes are. They're atoms of the same element that have the same protons but different number of neutrons. And we should be able to differentiate these isotope symbols, right, where we're writing the mass number on top and the atomic number on the bottom. And I want to point out that this is flipped from what is on the periodic table. On the periodic table, it has the average atomic mass on the bottom and the atomic number on the top, but this is flipped for isotope symbols. Okay, so that's about isotopes in general. But now, since we know there are two stable isotopes of helium, helium-3 and helium-4, when we look at the periodic table, it only gives you one number for the atomic mass. That number is 4.003. And how they get that number is they take what's called a weighted average of all of the isotopes. So they take the isotopes that exist for that element, and they figure out what percentage makes up each isotope, and then they use that to average it out to get this average atomic mass. So the number that you see on the periodic table is the average atomic mass, and it is a weighted average of the masses of all the isotopes of that particular element. Whereas these numbers like 3 and 4, that is an atomic, that is just the mass number. And that's just the protons plus the neutrons. And it's specific to each individual isotope. So now let's take a look at how we could calculate the average atomic mass. And we do that using this equation. So we're going to write the equation. We're going to do the mass of our isotope 1 times the percent abundance in decimal form. So I'm going to write this as decimal 1, and I'll explain what that means in a second, plus the mass of your second isotope times its percent abundance in decimal form. So I'm going to write that as decimal 2. And that's going to give us our average atomic mass. Okay? So let's take a look at some examples that'll help us out here. So here we have the element copper has naturally occurring isotopes with mass numbers of 63 and 65. The relative abundance for copper 63 is 69.2. Find the average atomic mass of copper. So first I'm just going to figure out what I'm given here. And so I know I have my mass of our first one is 63 AMU. Okay? And it says that the percent is 69.2. Our second mass is 65 AMU, and we don't know what the percent is. But we do know something about percents that we learned in math class. We know that all percents add up to 100. So we can find the missing percent by doing 100 minus the other percent. So I'm going to do 100 minus 69.2. And that's going to give me 30.8%. And that's my percentage of my second isotope with a mass of 65. So now I have the masses and the percents, but now I have to take it a step further and convert that percent back into decimal form. So how we do that is we take our number and divide it by 100. So you can either divide by 100 in your calculator, or you can just move the decimal 2 places to the left. Okay? And this is going to give us that our decimal for this is going to be 0.692. And our decimal for our second mass is going to be 0.308. Okay? So now I have my 2 masses of my 2 isotopes, and I have their 2 decimals, and I'm just going to plug right into my equation. So again, our equation is mass 1, which is 63, times the decimal 1, which is going to be 0.692, plus mass 2 is 65, times our decimal 2 is 0.38. Okay? And now I'm going to start putting things in my calculator. So I'm going to put 63 times 0.692 in my calculator, and I get 43.6, plus I do 65 times 0.38, and I get 20.0. And notice I did the multiplying first, right? That's our order of operations. It's in parentheses. We do the multiplying first. And now we're going to add these two together, and we get 63.62 AMU. And this is going to be my final answer. Now, I can check that this answer makes sense because our 2 masses are 63 and 65. So I know that my answer has to be between 63 and 65. I also know that mass 1 has a greater percentage than mass 2. 69.2% is greater than 30.8%. So my answer should be closer to 63 than it is to 65. And that's what I found to be the answer. Okay? So I can tell that this answer is probably correct. So again, what I did here was first I listed my 2 masses, then I listed the percentages that I knew. If I didn't know the other one, which in this case I didn't, I had to do 100 minus the other percent to find the missing percent, because all percents add to 100. Then I converted my percents to decimal form by dividing them by 100, or moving the decimal place over 2 to the left. These decimals should give you a number that is less than 1, so it should be point something. Then I plugged into my formula, multiplied first, then added to get my answer. Let's try one more problem like this. Chlorine has 2 isotopes, chlorine-35 and chlorine-37. Chlorine-35 has a natural abundance of 75.77% and a mass of 34.696 AMU. Chlorine-37 has a mass of 36.966 AMU. And we're going to calculate the average atomic mass. So let's start off, just like before, by figuring out our masses and our percentages. So I know my chlorine has two isotopes, chlorine-37 and chlorine-35. And in this case, they give us a more detailed mass for each, which has a decimal. So that's what we're going to use. So chlorine-35, it says, has a natural abundance of 75.77% and a mass of 34.696 AMU. So my first mass is going to be this, 34.696 AMU. And you know AMU is the unit for mass, so that's how we know that that is the mass. And we also know that its percentage is 75.77%. Okay, so that's our first isotope. The second isotope, it says, has this mass of 36.966 AMU. And in this case, again, we're not given the percentage. So we know that percentages have to add up to 100. So I'm going to do 100 minus 75.77, which was that other percent. And I end up with 24.23%. Okay, now I'm going to take each one a step further by making this into a decimal. So again, you can divide by 100 or just move that decimal place over 2 points. And so my first percentage, 75.77, becomes 0.7577. And my second percentage, 24.23, becomes 0.2423. So now I'm set. I have my two masses, I have my two percentages, which I've turned into decimals, and so now I can start plugging in. So again, my formula is the mass times the decimal of one plus the mass times the decimal of the other. So let's take a look at our first mass is 34.696, and then I'm going to multiply that by its decimal, which is 0.7577. Put that in parentheses. Plus my second mass is 36.966, and I'm multiplying it by its decimal, 0.243. And now I'm just going to use my calculator to do some math. So first, again, I'm multiplying first. So I do 34.696 times 0.7577, and I get 26.3 plus 36.966 times 0.243. I put that in my calculator as well, and I end up with 8.99. And then when I add those two things together, I get 35.29 AMU. And that, again, is going to be my final answer. And now, again, it makes sense to check this, right? We expect our answer to be between 34.696 and 36.966. Our answer, 35.29, is between those two, so that is a good thing. And also, mass 1, that 34.6, is a greater percentage than mass 2, which is 36.96. So we would expect our answer to be closer to 34.6 than 36.9, and 35.2 is closer, so that checks out as well, okay? So when you're solving these kind of problems, what you want to do is find the masses of each isotope, then find the percentages of each. If you're missing one of the percentages, you just do 100 minus the other percent, because we know all percentages add up to 100. Then we take the percents, turn them into decimal form by dividing by 100 or moving that decimal place over 2 places. And then we use our formula to do the mass times the decimal of the first isotope plus the mass times the decimal of the second isotope. When we add those all together, we get our answer. And we can always check our answer by comparing it to our two masses of our isotopes, and it should be somewhere in the middle. Okay, so we've gone over how to calculate the average atomic mass. We've also gone over the difference between isotopes. They're atoms of the same element with the same protons but different neutrons. We also went over the isotope symbol and how that shows the mass number, which is protons and neutrons on the top, and the atomic number on the bottom. Hopefully this was helpful.